Now that we're armed with an idea of what power series are, and we have that theorem that basically says, power series, there are only three possibilities in terms of the values of x for which these series converge. Now we need to look at some examples, right? Because that's when you really see everything coming together, right? So in each of these, here's what we're going to do. Let's write down our objective for this video. We're going to be able to find the interval of convergence and radius of convergence of each series, right? So radius of convergence of each power series. All right, so let's go. So here's part A. So here's our series. Our k goes from 0 to infinity. And what we have is x plus 2 over 3 to the kth power. All right. So this doesn't necessarily look like our original or our definition. So let me just show you again how we can use some properties of exponents to kind of put it in that particular form. So k goes from 0 to infinity. So the first thing I'm going to do is I'm going to split it up so that we can see the coefficients and then identify the part of the power series that has a variable. And we can see the part right here, it's in the numerator, but I'm going to split this using some properties of exponents. So what I can do is I can write this as x plus 2 to the k over 3 to the k. So the part that doesn't have the variable x, those are going to be our coefficients. So I can write that as, in fact, I can write that as 1/3 to the kth power. And then the other factor here, the numerator, I can write that just for emphasis as x minus -2 to the kth power, right? And using our notation from our definition, this would be our c sub k, right? So those would be the coefficients. And then this would be the a, and that would be the center of our series, right? So our coefficients are 1/3 to the k, and then our center is at -2. All right. So how do we figure out this interval and this radius of convergence? So this is where we have to rely on, again, what we know about infinite series, meaning going back to the geometric, maybe not so much telescoping, all those tests, right? Now, if I look closely at this, and here's another way that I could write this out in sort of the long expanded form. When k is equal to 0, this expression is equal to 1. When k is equal to 1, that expression is x plus 2 over 3. When k is equal to 2, then I'll have x plus 2 over 3 squared, and then the next term will be x plus 2 over 3 to the third power, and so on. I don't know about you, but this looks and it smells like a geometric series, right? So because this looks to be geometric, right? So this is geometric. The first term is 1, right? And then the question is, what is our r? Well, it looks like to get to the next term, we keep multiplying by the quantity x plus 2 over 3, right? Seems like each time we multiply by the quantity x plus 2 over 3, and it generates the next term. The difference now is that our r has the variable in it, but it's still geometric in its pattern, right? So, how is this helpful? Well, we know what is required for a geometric series to converge, right? In fact, to converge absolutely, right? Our R has to be strictly between plus or minus 1. So, for absolute convergence, let's fix this. So, for absolute convergence, remember, there are two ways you could say. You could say that the absolute value of your R must be less than 1, or equivalently, you can say that your R has to be strictly between plus or minus 1. It can't even be equal to the endpoints. So I'm going to use this version of it and set up a nice inequality, and we should be able to solve for x, right? So this means the quantity x plus 2 over 3, that must be less than 1. So since I'm trying to figure out the values of x, right, that's going to give me this interval of convergence. Let's isolate the x. So let's multiply each part of this compound inequality by 3. So negative 3 is less than x plus 2, which is less than positive 3. And then let's subtract 2 again from each part of this inequality. So subtracting 2 from this gives me negative 5. Subtracting 2 from the middle piece, the plus 2 goes away. Subtracting 2 here gives me 1. So this tells me that this series, this power series, even though it's not written in the standard form, but we can put it in the standard form. This power series converges absolutely whenever x is strictly between negative 5 and 1, right? And we can actually sketch this interval, right? Here's how we would sketch the interval. It goes up to, down to, and not including negative 5, up to not including 1. And here's where the center is useful. So if you notice, the center is exactly halfway between these two numbers, right? If you take the average of negative 5 and 1, you're going to get negative 2. That's our center. And then to answer the second part of the question about the radius is the distance from the center to either one of the endpoints. So I'm just going to indicate it right here. This is our R. And in this case, R is 3. Right? That distance here, if you take 1 minus negative 2, you'll get a 3. Notice if you take negative 2 minus 5, you'll also get the 3. So here is our summary. So the interval of convergence is negative 5 less than or equal to x, which is less than 1. I'm sorry, no, equal. It's negative 5 less than x, which is in turn less than 1, with a radius of convergence of 3, right? And we got that because this was geometric. So we got to use everything we know about the geometric series. It's helpful because essentially our test for the geometric series gives us the interval of convergence. Okay, so let's take a look at another example. This one is going to be a little bit longer. It's going to be a little bit more involved. And part of the reason is this one is not geometric. All right, so here's our series. K going from 0 to infinity. And let me write it out this way. So we have negative 1 to the k, and then you'll have x to the k. There's our variable now. And then we have 3 to the k times k plus 1. All right. So again, just to put it in that standard way of writing a power series so that we can identify the coefficients and we can identify the center. There's not much to do here, but here's how we can write it out. So to identify the coefficients, look at all the terms, all the factors that don't involve the variable x. So that's the -1 to the k, and then all the terms in the denominator, right? They don't have an x. So this is 3 to the k times the quantity k plus 1. And then now this other part here, again, when we wrote up our general definition of a power series, we had x minus a, that quantity, all to the k. Well, I can write this as x minus 0 to the k, right? So that helps me identify this as these are my coefficients. So those are the c sub k's. And then here is my center at a equals 0. So in fact, because the center is 0, this one can be classified as a Maclaurin series, right? So this one we can say is a Maclaurin series. Again, does the word really affect what we do? No. All right. So this one definitely isn't geometric, because if you look at the coefficients, you can see that yes, you have this to the power k, this to the power k, but then you're multiplying the 3 to the k by a factor of k plus 1. So unfortunately, this is not geometric. Well, what can we do? Well, what we can do is we can apply something like our root test, for instance, or our ratio test, and go for and test for absolute convergence. Now remember, for absolute convergence, we have to look at the series of absolute value terms, right? So the series of absolute values, and then we're going to see if we can apply this. This new series can be applied to any of our previous tests, right? So this is what we're going to go for. So for absolute convergence, because that's what we want, right? We're going to look at this series. So I'm just going to put absolute values around everything, and then as we did in the past, we can simplify as much as possible. So we have 3 to the k, and then k plus 1, like this, right? Okay, well, because of properties of exponent, well, that too, and absolute values, however, we can split our absolute values up like this. We can take the absolute value of the -1 to the k. We can then multiply that by the absolute value of x to the k. We can then divide that by the absolute value of 3 to the k. And then finally, the absolute value of k plus 1. Now, let's start with this factor here. We saw this back when we were doing our alternating series test. Taking the absolute value of something like -1 to the k or -1 to the k plus 1, that's always going to be equal to 1. So this just simplifies to 1. That helps a lot. I'll leave this factor for last. 3 to the k is always positive. So I can drop the absolute values, and that just simplifies to 3 to the k. For k going from 0 to infinity, k plus 1 is always positive. So that, again, I can drop the absolute value, and I can make it just k plus 1. The problem, though, is my x, I don't know if my x is always positive or negative, right? So I can't drop this absolute value. So the most I could do here is say that here is the series of the absolute values, right? This will just be, I'll have the absolute value of x to the k in the numerator. And then in the denominator, I'll have 3 to the k times the quantity k plus 1, right? So what I'm going to do now is apply my ratio test to this, right? And the ratio test will work because, again, a lot of common things will cancel out, and it will leave a fairly simple ratio that we have to compute at the end, right? So using the ratio test, remember what the ratio test says is take this as your a sub k, now that everything is positive, right? Take this as your a sub k and divide your a sub k plus 1. So we're going to set this up first. So when I replace all the k's with k plus 1, I'll have the absolute value of x to the k plus 1 over 3 to the k plus 1 times the quantity. And when I replace k with k plus 1, I'll have k plus 1 plus 1, so that's k plus 2. And then I'm going to multiply by the reciprocal of this. Remember that trick? Since we're dividing by a fraction, we can multiply by its reciprocal. So 3 to the k times k plus 1 over the absolute value of x to the k. Okay, so how is this going to simplify? Well, I can write this as x times x to the k in absolute value. And then the numerator here, I'll have 3 to the k times the quantity k plus 1. And then this is all over in the bottom. I can write this as 3 to the k times 3 to the 1. And then times k, the quantity k plus 2. So we completely get rid of this, right? Oh, and I forgot one thing in the denominator here. I need times the absolute value of x to the k. That's a pretty important piece. Now, using another property of absolute values and exponents, you get the absolute value of x times the absolute value of x to the k, and then we're left with the quantity k plus 1. And then in the denominator, we have 3 times the quantity k plus 2, and then we have the absolute value of x to the k. So something else cancels out, right? We got a common factor here, common factor here. Things are looking good. Now, as far as reducing this further, I think we've pretty much hit our limit. No pun intended. So what we have is the absolute value of the quantity k plus 1 over 3 times the quantity k plus 2. Right? Now remember what the ratio test says. We now have to compute our r. So let's compute the r for this. So it's the limit as k goes to infinity of this expression. And I'm going to write this intentionally in this way. So we're letting k go to infinity. This factor here does not include k, so it's treated as a constant. The only thing that's changing is this that I have in parentheses. So I can factor out the absolute value of x over 3, and then we're left with the limit as k goes to infinity of the quantity k plus 1 over k plus 2. But using dominant terms or using L'Hopital's if you'd like. Let me throw some L'Hopital's in there. You'll have the absolute value of x over 3 times the limit as k goes to infinity. The derivative of the numerator is 1. The derivative of the denominator is 1. So what happens here is that this limit reduces to x, the absolute value of x over 3 times 1, which is the absolute value of x over 3. And that's our r. But what does the ratio test say? The ratio test says that for us to have our absolute convergence, right, R has to be less than 1, right? So for convergence, in fact, let me say absolute convergence, the ratio test requires that whatever we get for R, it has to be less than 1. And what happens here now is because our series now involves a variable, it is going to allow us to solve for that variable. So this R must be strictly less than 1. And we have to solve this inequality for x, right? So it's a good exercise. It's a good reminder, again, of how to solve absolute value inequalities. So if you have the absolute value of x is less than 3, if you drop the absolute values, right, trying to isolate the x, then this is equivalent to saying that your x has to be strictly between -3 and +3. All right. Now, we can't call this the interval of convergence. And the reason why we can't call this the interval of convergence is because the ratio test, it fails when our R is equal to 1. So we don't know what happens at the endpoints. What we can say from this, however, we know the radius of convergence. So I'm going to draw that interval, and I'm going to put a -3 there and a +3 there. And here's our center. Remember, we found our center to be 0. So for sure, we can say that the radius of convergence is 3. What we don't know is what is happening at that endpoint, or what is happening at that endpoint. So here's where the question goes on a little bit longer. What we're going to do now is to test to see what happens to the series specifically at these endpoints, right? So for that, we're going to go back to the original series, right, a power series. So let's say this, let's start with the -3. When x is equal to -3, I'm going to plug -3 into our original series, and we might have to apply another test again. Let's see. So when x is equal to -3, we have -1 to the k, and then times -3 to the k, and then that's all over 3 to the k times k plus 1. Well, let's carefully simplify this and see if we can identify this type of series. Well, in the numerator, I can use another property of exponents, that because the powers are the same and I am multiplying, I can multiply the base. So I can write this as -1 times -3 all to the kth power, and then that's over 3 to the k times k plus 1. Well, -1 times -3 is a +3. So I have a +3 to the k in the numerator. I have a +3 to the k in the denominator. Well, those common factors are gone. I can reduce my fraction to 1 over k plus 1. All right. Well, what is this? It looks a little strange, but this one, I'm going to rewrite it. This is our p-series. This is our p-series with p equals 1. In fact, it's our famous harmonic series, right? So this is p-series, p equals 1. So I'm just going to remind you that that's the harmonic series. But we know with a p-series with p equals 1, this series diverges, right? So this one diverges. So at the left endpoint, it doesn't quite work, right? Because we end up having the harmonic series. Let's check the other endpoint and see what happens then. So when x is equal to positive 3, something similar is going to happen, but it's not going to cancel out exactly the way we anticipated. Because what happens is now you have negative 1 to the k times 3 to the k over the same 3 to the k times the quantity k plus 1. Well, now the 3 to the k's go, but I'm still left with that alternating factor. So 0 to infinity, I have negative 1 to the k, and then I have 1 over k plus 1. And I can do that same thing. I can start the series at k equals 0, or I could start it at 1 and then subtract 1 from the summand. So this kind of shifting of our index, it's the exact same series, but the reason why I'm doing this is so that you can see that now this is the alternating harmonic series, right? So this is our alternating harmonic series. And if you remember that the alternating harmonic series, this one converges conditionally, right? We even used it, and when we showed the consequence of conditional convergence. So please, if you don't remember that, you can look back in your notes or go back and look at the corresponding videos just from a few videos ago. But the alternating harmonic series, this one converges conditionally. So converges conditionally. So putting this all together, right? So this series, or let's say this power series, is centered at 0. So is centered at 0 with a radius of convergence r equals 3 and an interval of convergence. Now let's be careful when we write this down. Remember, with at x equals negative 3, the series diverges, so we can't include that in the interval. So it's open at the left endpoint, but because at x equals 3, it does converge, even though it does so conditionally, we can include the 3 in the interval. So it's less than or equal to 3. If you prefer to write your intervals in interval notation, then this is what it would look like, right? And there we go. So yeah, that was quite the journey, but what this shows is that we can utilize what we know about series from our previous work. We just now have to modify the way we think, since our power series, they include the variable x, right? So hopefully those two examples help. We can see once again that the geometric series is relatively easy to work with, since it already gives you the interval. But when you're applying things like the ratio test or possibly the root test for the absolute convergence, then you might have to do a little bit more work. Plus, we have to check each endpoint because we don't know in advance whether each endpoint will result in convergence or divergence. So hopefully that helps, and I'll see you in the next video.